Okay. Okay. I suggest we start. I would like to plan the day today as follows. I thought that we would give as much time as needed to present the real-time algorithms and to finish that. And then if time is left, I would love to drink a coffee with you at the cafe next door. But let's hope that we manage in time, which will hopefully be at around 3:15 that we can move. There's another announcement I wanted to make, so to be sure that I don't forget it, I want to send you an email about it also because some of you might be interested in an event that takes place in October 5 and 6. I mentioned it already, I think. It's the Airborne Wind Energy Conference 2017. It's about airborne wind energy, which I think I explained at some point at the beginning. So there's a lot of optimal control involved, but of course a lot of other things as well. And if it's interesting to some of you, then the following thing might be interesting. We open, I think, 10 scholarships for reduced registration for this conference, where a student would get the 2 days of the full conference, October 5 and 6. It's 2 weeks before the semester starts, for €30 instead of €300, which normal participants pay, or now they pay already a bit more because the early bird is expired. So this is on application. There's a web form. Deadline is next Monday, and I will send out the link to every lecture I have. And you will be, so to say, invited by our lab, but it's only students that do either a bachelor or a master at University of Freiburg that are eligible to this. So just in case you're interested in airborne wind, this would be now your chance to apply. And then this was everything on the announcement side. The exam, I think everyone knows about the exam. When it will take place, do you know about the date? It's September 2022. At what time? 2 o'clock, I think? Right? Good. And then there was also one organizational thing. I think at least one project wanted to say a few words about what they will do, right? Mm-hmm. So I suggest we do that at the end of the lecture, before the coffee. And is a time slot of 5 minutes enough for that? Or maybe even less? Perfect. Mm-hmm. Good. No other project, I guess. Yeah. Okay, so then let's start. We are still in chapter which I called, it's called chapter 16, about parametric optimization. And the task that we want to address here is actually, we start with a parameterized optimal control problem. And this problem we can denote by something that I denoted last time. So we have optimization variables and objective constraints G of W and P and H of W and P that are smaller than 0. But what we are really interested in is to regard this optimization as a feedback generator for model predictive control, so that the input here is a P and the output is a W star of P. Yeah, and this solution manifold, as I depicted last time, if you try to plot it like what is this W star of P as a function of P, then it might be something that is non-smooth and might have these kinks at active set changes. And that's creating a lot of difficulty here. And for this reason, we treated first the case where we would not have these kinks, but where we would have a smooth manifold. So we basically said, let's assume we have something smooth. And roughly speaking, what we said, we would just get to some system R of Z that still depends on the parameter, and that is equal to 0. And in order to give you directly now an example of how such a smoothness could be generated from the problem data, I want to go to the interior point formulation with a fixed barrier parameter. So one option for this R would be that the variables are Z as actually W, lambda, and mu, and in this case also maybe the slack variables S. Yeah? For each inequality we add also a slack, and then this R of Z and P would still depend on the smoothness parameter tau. You remember this smoothness parameter that we introduced in order to relax one part of the KKT conditions. And then the optimality system for the interior point method here would be one where we say it's the Lagrange gradient, which depends, of course, on all these data and on P possibly, right? So I should put the P here. That should be 0. The equalities should be 0. Sorry, this is all R. That should be 0, but I don't put it into the vector, of course. So H of W minus plus S should be 0. And then the product of mu 1 times S1 minus tau up to mu NH minus SNH. I mean the number of inequalities that we have. So this could be an example for such a root finding problem, where the variables Z are now given by all these numbers here. So that would be one example for a fixed tau. I stress this because for a fixed tau, this is indeed a smooth system, right? If tau is a positive number, then we know that these solutions will be nicely and well behaved. If you put the tau to 0, then of course this would get a very nasty system, because this constraint that this means should be 0, that just corresponds to the set that is depicted here. And if you would then include the inequalities which are not present here, it would just mean the non-smooth set, and then we would have a kinky manifold again. So I just wanted to stress this fact that the tau needs to be positive in order for this system to be really smooth. And if you want to depict what this manifold would look like for a tau that is small but positive, then this manifold would be something that looks similar to the true one, but is now a smooth version of it. Yeah? So this would be the manifold that you would get from R of R tau Z P equals 0. So that would be the 0 level set of that function in the space of W and P. And this would be the true solution. And now this curve is for W. So I just wanted to tell you with this that this RZP is not completely artificial. I mean, it's not something like a complete toy problem. It's something that you can indeed generate by making your nonlinear program smooth by making some form of barrier formulation. And that's indeed done in some approaches. And I just give you some literature links here. There is a paper by Otsuka, which basically, I mean, it's not exactly this method, but it's more or less doing something like this. There's a Boyd and Wang paper, I think from, I forgot the date, maybe 2008 or something, maybe 10, I guess. I don't know. Let me just put a question mark here. So this approach is sometimes taken, and once you have it smooth, we introduced already, so this was, by the way, this was new stuff, now I repeat again. So then our philosophy was to at whatever point we are in this combined space of W and P, we actually use the latest linearization point in order to get the next one. And maybe I should also clarify what was the task that we really want to address. As I said, we want for a given P a new W star of P. But basically, we expect that there will be a sequence of incoming parameters P, like initial values of the real system. For every new initial value, we want to solve this problem, but we expect these parameters to so to say, move in one direction, so to say. I mean, they will not randomly jump. There is a high-dimensional parameter space, but they will probably be related to each other. And so it makes sense to really work with derivatives and with continuation methods. So the assumption is, so to say, that there is a sequence of incoming parameters of incoming parameters pk, pk plus 1 and so on. which are close to each other. And then the idea that we had already, this predictor-corrector form, predictor-corrector iteration. This was maybe to remember, it is for a given guess that we had. So we have a given pk and a given zk. I mean, the pair of the variables. The problem instance is given and an approximate solution to it was given. And now we want to use that guess to generate a solution to the new problem, which has the parameter pk plus 1, which is similar. We linearize, and what we actually, we get this r of zk pk, and I drop the tau now. That was just one example, right? And here we have the r. I put maybe the derivative now at the bottom. So we have rz of the same arguments. It will always be zk pk, so I drop it now, but multiplied with zk plus 1 minus zk. So that's defining the next zk plus 1, plus rp, the derivative of this thing in the direction p at the same point where we are. And then this will be multiplied with pk plus 1 minus pk, and that should be equal to 0. That's the philosophy, and that will implicitly define zk plus 1. And we wrote down already an equation for that, but I don't need to repeat it. You can interpret it, as I said, into a kind of here we are, then there is a kind of corrector step that brings us down to the manifold that's due to this term. And there is also a predictor step when this was pk, and this, for example, would be pk plus 1. Then the predictor step would then lead us to this point, and the predictor step is due to that term. And now the question arises, how close are we to the solution manifold? And there is one result that I want to cite, which I could prove, or we could prove, and maybe we can do it as an exercise later together in a discussion at the coffee break. But the result is actually that the distance of, we should also define z star of pk, right? So that's the true solution. That's what we would like to be close to. That is the one that solves for a given pk the problem. And then one can establish the following, that we get the distance between the new iterate, this thing that we just defined via that linear system, and the true solution at the new parameter value pk plus 1, that this thing is bounded, or maybe I actually write it in order form, is actually of order of two distances, namely the distance that the old point, the old iterate had from the corresponding solution. So there was an error here. We were not exactly on the manifold. And the other part is that if we do a step, pk minus pk, so if we change the problem, and this to the square. So it's actually, in the spirit of a Taylor approximation, this is a Taylor approximation of the whole problem, so it's only logical to expect that the error we make is of second order, but in order to really bring it into this form, one needs to do some formulations that I don't want to do now. But this one is something that one can show, and this implies a few things, and maybe if you just look at it, so roughly speaking, it says that this is smaller than a constant times the square of this. If we don't change the parameters here, I mean, if we would just keep iterating with the same p all the time, it would just mean that these terms would be 0, and then it's basically saying that we have quadratic convergence. That's what quadratic convergence means. That's what we would expect for Newton's method. And indeed, if this term wouldn't be there, this is just the equation that we need to solve in the Newton's method. So I said already, for pk plus 1 equals pk equals all the same, parameters are the same, pk plus 1, if they are all the same, get quadratic Newton convergence. that's just, so to say, a corollary of this result here, if you want to say so. We proved that before, of course. And the other thing is, if we get this point, if we started on the true manifold, if the zk was already equal to that, then this term will be 0 anyway. And so what we then get is actually what we derived already last time, the fact that this zk plus 1 is actually just the tangential predictor. Yeah? Because what is a tangential predictor? It means that the error with respect to the true function is of second order. So basically it just means that the zk plus 1 is the derivative. Yeah? So for zk equals to z star of pk, get a tangential predictor. So to plot it in this landscape above, maybe I plot these two situations in a zoom. So here's my current iterate. This was zk and pk. This is p, this is z. If you don't change the pk, then the first Newton step would maybe be here, second maybe here, and so on. So you would just iterate towards this, but with quadratic rate of convergence, so it's difficult to plot it even. I mean, after the second iteration, it would be on the blackboard already at the right point, I guess. So that was this first situation, A. So here we have A. The second situation would occur if we are, for example, here at this point. Let's plot it here. So then we are exactly on the manifold already. So this is like case B. And if we are exactly on the manifold for a given value pk, and here's our value pk plus 1, so this one, then, okay, this is too, maybe I plot it a bit closer here, so that I still have a chance to get it, and then we get here the tangential predictor. This point here. And maybe I should make the manifold smooth so that in theory this result holds, right? And you see from these plots already that I'm very unhappy about these curvatures, but that's actually once you have a nonlinear function, then you will have curvature, and linear prediction can only be good in a neighborhood. So here you see that this quadratic approximation is really nice, and it gets very nasty once you get strong second derivatives kicking in. But anyway, it's a tangential predictor, and it has, for small pk plus 1, it has this property, and for any one, that's what the order says, right? So, of course, this is most interesting for very short, small changes. So if the pk plus 1 would be here, everything would be much nicer. Okay, so that's a basic result, and you can now use algorithms with this spirit, as I mentioned here already. And in particular, the method of Otsuka is one of the very widely used real-time algorithms, is basically doing an iteration of this form. So that is something that you can do, and a lot of MPC algorithms that, so to say, don't explicitly treat inequalities are of this similar form. So now you could say this is very unsatisfying because you do not deal with these active set changes in a form that is actually, for example, interior point methods, they start with a big tau and then they make it smaller. So these are things that we don't exploit here, and one can exploit them in different ways. And one second way, which is also quite clean and easy to explain, even though I don't favor it, I want to explain now. And so I just give some examples building on this idea. So Otsuka, as I said, it's a Japanese researcher who wrote a nice code-generating solver, and there are lots of other details. But it's basically something of this form from our perspective. Then there is, he calls it the C continuation GMRes method. And the reason why he calls it GMRes is because he solves this linear system with GMRes, an iterative solver. Also, maybe I should mention that he uses single shooting. It's a single shooting, or it's a sequential formulation. It uses reverse AD. He doesn't call it like that, but it does. Reverse AD for the gradient, and then this type of predictor corrector path following. There is another algorithm that's called the advanced step controller. I want to mention. It was introduced by two researchers from the US, Spiegler and Zavala. And the advanced step controller is actually something, so this would be one example. Second one, what does it do? It will actually solve the full NLP first, but it solves it for a problem that is at the, it uses this prediction that you think that if I have solved that problem, I will be at that state. So you solve it for the state where you expect that you will be in, let's say, 2 seconds. You solve the full NLP that you think will be solved then. But then you have basically obtained 1 point on this landscape. Yeah? For example, this one. Once you arrive after 2 seconds, you can take the real measurement of your state, and once you see that this state is maybe wrong, it's maybe not this one but something else, you could still use the derivative result that you can cheaply get from the interior point method as well, in order to get at least a first order feedback in the same spirit as this one. But you do it for actually a very small barrier parameter, so if you're close, so the manifold to which you'll solve your problem is, so to say, nearly non-smooth. So it will have some difficulties if you are close to such a point, because then you will get this large overshoot, right? But anyway, so that's a method. So the idea here is to solve NLP for a predicted parameter. Then you get this is an implicit function theorem basically. It's just this result when this is already 0, right? Get sensitivity dw star by dp of p, and you can get it actually from the KKT matrix. So it's something that is not too difficult to get. I mean, it's basically inverting this matrix, and that is the KKT matrix. And at the end is when the real parameter, I mean, maybe I call it for predicted parameter p bar, yeah? And when the real parameter P real is known. So compute the tangential predictor. And what you do then is actually you give the z that you will actually give. Maybe I call it, I call it P plus because it's the next one. Yeah. So you can say Z plus is equal to Z star of P bar. I mean, that is the solution that you computed in the first step, right? Plus a correction, which is this dw star by dp at P bar that you computed also before, times P plus minus P bar. That is the tangential predictor. And that is basically, if you are on this point here, would be, if this would be, maybe I call it P bar, and this would be P plus, then you go to that point here. So that would be Z plus. So you get the tangential predictor. So these are 2 algorithms, and there are more that just use, so to say, the first order predictors in the unmodified sense, but there is another form how to deal with the inequalities that is trying to overcome the problem that you have that these non-smooth points will always be, because non-smoothness is like the strongest nonlinearity that you can have, right? I mean, all derivatives blow up to infinity. So you could actually try to treat this differently. And this is what you can do when you define things that we call generalized tangential predictors. Yeah? And in this case, you solve, like in an SQP method, you solve a QP in each iteration. So here, we could also say, let's not solve just a linear system in each iteration, but you could also accept that we solve a QP iteration in each iteration. So the alternative is to use generalized tangential predictors. Yeah, so this is a tangential predictor. Sorry, this one is a tangential predictor, but we can also get generalized tangential predictors. And in order to explain that, I think I would need to come back to this and think of this being solved with an SQP method. And it gets a bit simpler to write down, and that's what I will do now. For notational simplicity, but only for that one actually, I will assume that a P enters linearly, only the function G enters linearly and only into G of W and P equals 0. And maybe I should say that you can, in principle, always get that by just including the P as a variable into your optimization problem. So you could say my variables of the above problem here are W and P. Yeah, and then my equalities would be the original ones that I had, plus the equality that says P should be equal to P bar, and P bar is now the parameter that enters my problem. So this way I basically augmented my variables, and then the whole notation gets simpler. So I will regard, in order to present that thing, which I think we will talk in the script, which is very preliminary, we will have that maybe in section, I think 16.1.3. Yes. Somewhere in 16.1.3. But I should say that this is subject to revision. In particular, also the numbering might be subject to revision. But what I want to write down now is actually the following. We have an optimization problem which depends on P. I call it now P, and it will just be of the form minimize W, F of W, subject to G of W plus a matrix M times P equals 0, and then H of W smaller than 0. So this would be a very slightly simpler notation. Huh? So I have now this derivative, this matrix M. In this case, would just be the one that multiplies with this P bar. So it has a unit matrix and a minus sign somewhere. In other cases, for the initial value constraint that we have in MPC, just remember that actually our first variable would then be equal to P, right? And then our other constraints are x, I1 of x0, u0, and x2 minus f of x1, u1, and so on. So these would be the, this could be, for example, a g of w plus m, maybe this would be g of w, and then M could be then the matrix which just has a minus unit matrix here and a lot of zeros. And then you see that G W plus M times P would just give me back the constraint where the initial value is constrained to be at the initial value. Do you follow? Was it two? Yeah. So I just wanted to say that our multiple shooting problem, for example, is already in that form, and we can bring every problem into this form by augmenting the variable space W to include also the parameters, and then have a new parameter coming from outside. But I simplify notation, so we have basically the same setup as before, but with a slightly different way how the P enters. And so we are still interested in the solution WST star of P. So now with this change of notation, things get a bit easier. because I can now easier write down the QP in an SQP method that we know already, and I use one with exact hash to make it completely a second order predictor method. And so what this will be, it will be some QP which depends of course on the linearization point. So it's, the problem is minimize W. Here will be the gradient of f at wk. I give it already an iteration index, right? Times w minus wk plus, and I think I need more space here. Maybe I should have left more space, but anyway, I think this will be enough. Plus 1/2 times w minus wk transpose, and here is w minus wk. And in the middle we have the second derivative of the Lagrangian with respect to w. And I call all the variables maybe z. Yeah, so zk is w, lambda, and mu multipliers. And then it's a shorthand. And please note that because of the fact that the second derivative of this whole thing, I mean, no derivative depends on p. So it's all a function of z, and I don't need to have the p included here. And then I have here my constraints, wk plus the derivative of the constraints. Maybe I write it in this form, dg by d, oh sorry, this is, yeah, dg by dw at the point wk times w minus wk plus, and now I keep the linear dependence here, plus p. Plus m times p. So this is still parametrically depending on this p. And my inequalities are now in this linearized form, dh by dw wk, w minus wk smaller than 0. So that would be a QP. If you think of what data do enter this QP, it's of course the zk. I mean zk comprising wk, which is the linearization point, and also the lambdas and mu's, which are only needed in the Hessian. And it also, of course, needs the p. And what will it generate? It will generate a new iterate in principle that gives a solution to all these things. And of course, it could be a prime or dual solution. And maybe I change my notation in the following sense, that I call this p now already pk plus 1. So I give this index pk plus 1 because it will be the one that is for the next problem. I have my last solution guess to have the problem for the next problem, and then it will spit out a zk plus 1, which consists of a wk plus 1, a lambda k plus 1, and a mu k plus 1. So you want to get out a complete solution. And so from this perspective, which is actually nothing else in the sense that than the philosophy of sequential quadratic programming, I just linearize my problem or do a quadratic expansion at my current guess. I use here the fact that my parameter enters linearly, so I can just linearize. I mean, nothing depends on the parameter. That's making my notation a bit easier. Otherwise, I would need to add a lot of sensitivities for the dependence on p here. And now I have a perfect, this is like the equivalent of that linearized system here. Here I have a linearized system that's for the equality constraint case that would be equivalent to that QP. But with the inequalities, I get these inequalities that a QP solver needs to address. And now I give this to a QP solver, and for the given zk and the given pk plus 1, it can spit out the next solution guess. And that solution guess, as I said, will be equivalent in case that I'm having a fixed active set, but it will be significantly different at the points where the non-smoothness comes. And that is the reason why this is interesting. And so one can again establish a result which is actually, it's the same formula as this one, so I don't need to rewrite it. I can just say here star also holds even at active set chains. So the only point where the other formula had difficulties is actually if you are on such a point. I mean, if you're really on such a point where the active set is, where there are weakly active constraints, and at this point, this method, depending on which parameter value you have, I mean, this could be the value pk, yeah, so this could be pk plus 1, or it could also be this one, pk plus 1, one of the two. And in both cases, because you solve a QP, they will have a different active set, and it turns out that the solution will be either this one or that one. Yeah, so it gives you a generalized tangential predictor, like a directional derivative in the direction in which you will move, that can deal with active set changes. And of course, in reality, it will you will never be on this point. You will probably be in the neighborhood. But in reality, it will look like this. So you are, for example, at this point. Now, this QP implicitly approximates, of course, something like a tangential predictor. So that would be the solution set of your QP for small changes. But because a QP will have an active set change when you do a larger change in your parameters, it will also have a prediction that there will be some active set change. So it will actually represent the whole nonlinear manifold by something that's a bit more general than this tangential predictor here. I mean, it's not just pure tangential predictor, but if your QP has an active set change, it will actually already, it will not maybe be exactly at the right point because you are not on the right point, but once you come closer and closer, it will be exactly at the right point, like here. But in general, your iterate would, for example, if this would be pk, and this would be pk plus 1, then your iterations would, this would be zk, and this would then be zk plus 1. Z or w, all the variables are piecewise smooth here. So you see that it somehow suffers less from the active set, from the non-smoothness. Yeah? So the bottom line here is you can jump across active set changes. And if you combine this quadratic predictor or this generalized tangential predictor with the fact that you iterate only once per problem, and then you already have the next guess that you can then use as a linearization point for all these variables, then you get what we call a real-time iteration. A real-time iteration is a method, or the method would be characterized by one predictor corrector step per problem. But it's based on a QP. On this QP, no? On QP star star. And of course, this can come in many variants. You have seen already, or I mentioned that here we have the Hessian of the Lagrangian. This Hessian can be indefinite. We usually don't like that. And in the case of model predictive control, very often people have quadratic objectives, tracking objectives. You just want to track some reference of your system, some trajectory. And in that case, we can easily use the Gauss-Newton Hessian. And then very often in implementations, you use the Gauss-Newton Hessian. It's cheaper and it's positive definite, or semi-definite at least, to get convex QPs. And now you could, of course, say, this is a bit funny. Now you use these Gauss-Newton Hessian, then you have this matrix wrong. What you will then get is an inequality that is not exactly like that one, but it's actually not quadratic anymore because we have a wrong derivative here, but it's still close to that expression. We call it approximately tangential predictors. I mean, they are not really tangential, right? Get approximate generalized tangential predictors. Okay. So why did I explain that algorithm so much in detail? It's the one that we distributed on the sheet. I think last Monday we distributed a sheet. Was it last or this Monday? Which was a complete bonus point sheet. But that was a sheet where we would actually implement the Gauss-Newton Hessian with a QP in order to do a real-time iteration. Of course, this algorithm, as I presented it here, is actually the one that doesn't perform a shift in time. I mean, we just regard an NLP that depends on the initial value, and that's it. Yeah? So in principle here, the variables W, K will just be used with the same time ordering as before. But there exists a variant where you would also change, so to say, the variables in each iteration by a shift. So you can have, here we have a warm start, pure warm start, but also shift is possible. You remember we discussed this possibility of a shift, where you shift the variables in order to take account of the fact that the horizon actually moves in time. Okay, so now you have an idea of what is the algorithm that I would actually prefer to use for nonlinear MPC problems. It needs to solve a QP in each iteration, and it needs to solve and it needs to generate all these derivatives. I mean, you need to prepare the data of the QP, and then you need to solve the QP. So both things are expensive. Particularly when you do it in a multiple shooting method, for example, then this means integration of your dynamics, differentiation of your dynamics, possibly second derivatives here. But the interesting thing is that when you don't know the pk yet, you can generate all these data already. So you need to know only the zk in order to generate all the QP data without knowing the pk. And then when the pk is known, then you actually add this little piece extra to your QP, and then you solve it. And so typically this is also easily combined with this philosophy of dividing into preparation and feedback phase for real-time iterations. We abbreviate them RTI. You divide the computations into a feedback phase, a preparation phase. So there is a preparation phase which does a few things. So what will it do? It will simulate dynamics. It will compute the derivatives, plus generate sensitivities or generate derivatives. And then it does also some things on the QP, because the QP can be pre-processed. For example, condensing. Yeah, I call it generally pre-process QP. For example, condensing. Condensing can be done mostly without knowing the initial value, and then you have already a small scale QP. And then in the feedback phase, when you actually get the new parameter, at that moment you solve a pre-processed QP. Yeah? So you solve a prepared QP. And this should be much faster than the rest of the computations in order to make sense, right? If this is the most computationally intensive step, the division doesn't make such a big difference. But if you have here and here sampling times, so if this would be pk, this would be pk plus 1. Yeah? So this is the arrival of the time points, of the data. It's a bit mixing. I think I mix. So this would be the time point tk, at which the parameter with the same index arrives, and this would be the time point tk plus 1. And what you do then is, until here you prepare, you pre-process the QP, prepare with the data that you have from ZK. And no, this is wrong. So you prepare here. And at that moment, you get pk plus 1. And you solve the QP. And then here's the feedback phase. And here can be the next preparation phase. So the answer to the new value pk plus 1 is obtained after a time which is significantly shorter than the full sampling time, or the full iteration time for one iteration of this method. Oh, this is a wrong plot, so this should be thick. Here's the small division. Maybe I should just make it red and green. So let's maybe make the preparation phase in green. So this is the preparation phase. It's from here to here. And then the feedback phase, where we solve the prepared QP, will be here. And here was the previous feedback phase and the previous preparation phase, and here's the next preparation phase, and so on. So this is how the algorithm would be divided in time. And hopefully this is, in some applications it's 1% of the whole cycle time, so it's significantly lower, and the feedback delay is therefore much smaller. And maybe I want to point out that also, of course, other algorithms, in particular this one, is also really divided into a preparation and a feedback phase, so I should also make that clear. Solve the NLP for a predicted parameter p bar, get the sensitivity. So this is all preparation phase here. And then when the real parameter is known, then you compute the tangential predictor. That's the feedback phase here. And this feedback phase is a bit cheaper, right? Because you only have to compute here matrix vector multiplication, while here we have to solve a prepared QP, possibly condense and so on. On the other hand, here you solve a complete NLP. This is a bit, and that can be very time consuming. So it might be many, like 5 or 10 SQP iterations that you need for that. So this could be significantly different. And then I also want to point out that, of course, the fact that here you solve a QP instead of a linear system like here is more expensive, but it allows you to basically get this effect. I want to stress this again. If you're close to such an active set change, and usually we have a lot of active set changes in MPC, then one method will just give you a complete linear tangential predictor, while the generalized tangential predictor gives you something that is already taking account of active set changes. So generally it's a more accurate predictor, a more expensive but more accurate predictor than a linear one. Okay, so this was a bit abstract, I think. But I want to invite you for questions. Yes?
Is the gain in accuracy compensating for the amount, for the additional complexity of computation?
It's a good question. And in fact, it's in order to really compare these things, I mean, for example, one should compare different algorithms, right? At the end, what matters is how much computation time you spend and what is the closed loop performance of your model predictive control scheme. I mean, it's a much more complicated comparison than if you, for example, just want to say what discretization scheme for ODEs is the best, then you could just say I discretize it with different forms and look at accuracy versus computation time. Here it's not accuracy of anything, it's actually closed loop performance. So the question if accuracy matters depends also on how accurate your model is. Yeah? So if your model of the real is accurate, actually it doesn't matter so much how accurately you solve these problems. What I can just say from own experience is that active set changes are like the one thing that we really, I mean, bounds are something we know about. Yeah? So it's one of the things we are most certain about. So it's a bit, it's intuitively a good idea to respect bounds in all iterations. But of course, a detailed comparison, because all these algorithms are relatively difficult to implement, was not really done yet in a systematic way, I would say. I mean, like in Japan, for example, nearly all application people I met are using this algorithm. Yeah, in America, people use sometimes this algorithm. In Europe, people use very often this algorithm. So it's just very different communities, and it's part of our ongoing work. And I think we asked already one master student to compare, for example, this algorithm, which is incredibly fast per iteration, with that algorithm, the real-time iteration and the CGMRES method. I don't know the outcome yet. Yeah. To compare it in closed-loop simulations. Okay, and there one could actually compare the time spent, the computation time per second. That's one measure. And you could, of course, tune both algorithms with sampling time differences. Horizons could be longer and shorter. I mean, there are so many things you can change that it's, so it's not only the algorithm, it's also the discretization scheme, the length of the horizon, and so on that you need to care about. So, yeah, a fair comparison should, for each algorithm, take the best choice. And in reality, what you will get is actually only a performance plot, which would somehow give something like average cost. The closed loop cost, and this would be the CPU time per physical time. I mean, you could have an algorithm that just does one iteration every second, or you could have an algorithm that does 100 iterations per second. This, with 100 iterations, would be 100 times more expensive, and you expect it to maybe get better closed-loop performance, maybe. So you would expect that somehow the cost would get lower when you spend more time, and you would expect for any algorithm something that would go down, and then the question is, where are the different algorithms? Yeah? So maybe for different numbers of iterations, different step sizes. So there are so many tuning parameters. So for every choice gives you some point in this diagram. And at the end, what I would be interested to know about is, where is this efficient frontier, the best choice for a given trade-off between CPU time and accuracy, or closed loop performance. So that would be the way to compare these things. But as I said, it's not yet done. This is just hypothetical comparison that could be done. And it's too much for a project, so I don't, maybe if someone wants to compare two things, it's good, but to compute this whole plot would be too much. Other questions? No? Yes?
Software frameworks.
Software.
Are there software frameworks that implement these algorithms?
Yes, that's a good point. I don't know so much about this one. I just want to say that people use usually IP-opt here, and then there's also some, I think IP-opt has some functionality to get these sensitivities out, so this is one way to go with IP-opt. These are scripts that you can find in Maple and Mathematica, I think, and maybe even MATLAB. So these are open source scripts that generate code, actually. They generate code. And this algorithm also exists in software, and the currently most used software for that is called Arcado. And that is code generating basically an SQP method with these characteristics. So Arcado is, has a MATLAB interface, and then you specify your model equations and so on in MATLAB. It spits out the QP and the derivative computations, and then you can actually use it from MATLAB if you want, or use it in Simulink and so on. And there is an ongoing development, maybe I should say, that is called Arcados, and that is what people in my team want to find as a successor of Arcado, which was developed by previous PhD students in my team, and it should be slightly different, but in the algorithmic framework it will be also very similar. Yes?
There is a tool called SIPO version.
Yes, for the sensitivities. So So SIP-opt is basically just giving you the sensitivity that you need here at this predictor. It's not rocket science. It's basically the inverse of the KKT matrix times some vector that gives you these sensitivities. Okay, yeah, maybe I should also say that what you can do easily yourself now with the tools that we have taught you in this course, you have Casadi, you can simulate an OD, you can get derivatives, you have QP solvers in that environment, so you can easily code yourself, for example, a real-time iteration. You could also code, okay, this one I didn't explain, so you cannot code it, but this one I explained basically in detail, right? I mean, there are no details left, I think. Just setting up this QP with a Gauss-Newton hash and solving it for different parameters. But it will not be as fast as, for example, a code-generated code, of course. I mean, it will still be with this MATLAB overhead. And if you have a code-generated code, I mean, there are some applications where this was run on a desktop PC with a microsecond sampling time. So you can solve then a QP and generate the sensitivities with just 1 microsecond computation time for very small scale systems with 2 states or something. And usually in many applications that we work with, this takes like maybe 20 milliseconds or such per iteration, and then you have maybe a full a robot model or such more interesting dynamics with 20, 30 states. Yeah, I didn't present, or I don't want to present many more details here. I think this is a good moment to stop. We rushed through a lot of optimal control, I think, in this class. And I tried to give you an idea of a lot of ideas that are also dear to me and that are interesting to be continued in PhD and master theses that are running in my team or in teams of people that are working together with us, or in the same community at least. And I could just say that at the moment it seems that the market for people that work in particular on real-time optimization seems to be booming, and there's, so to say, a lot of applications pull. I mean, there are industrial partners that want to hire my PhD students before they finish. And also there are some industrial applications, for example, that just use this Arcado. They don't want to be disclosed and so on, but it's running in some engine controllers and so on, even in production of cars or such things. Yeah? So it's really interesting what is going on at the moment in this domain. There's also a startup in Zurich, Embotech, which probably is currently recruiting. I don't know in which state they are currently. It's up and down like startups are, but anyway, it's an hot area. In particular, this thing when you do real-time optimization and you solve these problems fast and on embedded systems, that seems to have a lot of application pull at the moment. Just to give you some motivation to study for this. And now I want to end with a short project presentation, and don't be too long, but just tell us what is the idea of what you do. Maybe we close the recording now. Yeah. Maybe I thank you already for the lecture. It was a pleasure to teach to you, and I'm looking forward to drink a coffee after that. Thank you.